Hey folks, welcome back to Advent of Code in F#. Day 23, we're in the final 3 days, which is cool. We're almost done. It's almost February as well, so that's a good thing. Then I can move on to other kinds of projects. So yeah, let's take a look at day 23. There we go. I took a quick read of the exercise, but we're doing day 23, a long walk, where we're given a map, and we have paths, forests, and slopes. And the slopes have a direction, one of the 4 cardinal directions. And we start somewhere, we want to get somewhere else, and we are looking for the longest path. So that's a cool twist. It's not the shortest path algorithm, but the longest path algorithm. And it's just a basic search where you have walls and empty spaces. But if we land on a slope, we have to move in the direction of the arrow. So if we're right here, we have to take one right. That's the only way we can go once we're on that slope. And we would never step onto the same tile twice, so that will probably cut out a lot of the search space, or at least for the example, it'll cut out a lot of the search space. Maybe for this as well, yeah. So we will have a... Actually, that makes a lot of sense. Otherwise, we would have loops and infinite loops, and we would never end. So we would have an infinitely longest hike. So yeah, this is what we have to work with, and let's figure out how many steps the longest hike is. As I can see here for the example, there's actually not that many possible paths. There's only 1, 2, 3, 4, 5, 6 different paths we could take. Interesting. And the longest one is 94. So we have a lot of data to work with to verify our algorithm. I've never written a longest path algorithm, I think. So this will be interesting. Let me get rid of everything. There we go. As always, I grabbed my input and the example, and let's start first by the example. It's just going to be a path algorithm, longest path algorithm. So I'm just going to parse into a 2D array, as we have been doing for almost all of the graph puzzles this year. So let's do that yet again. No. I'm gonna... what was I going to do? I don't need the indexes. I was going to calculate the row and columns, but we don't need to do that. We just need to take the example, that's a list of strings, and map that's it, and put it in an array2D. So now we have a 2D matrix representing our grid. We could let's parse into something other than a character. So everything, what are the different options? We could have what's the free location called? Path, or forest, or a slope of slope kind. And let's define slope kind. Or let's keep the character value in there because it reads nice, those 4 directions. So a cell is one of those 4 things. Let's parse into this thing. So array2D map. To transform every element, we get the element and we return the element. So we can write a parse cell function. It takes a character, so if it's a dot, we have a path. In this case, we have a forest, and in the 4 slopey things, what's the slope downward? It's a V, okay. That's a slope V, or let's just wrap slope into its slope, and that's good enough. And we hope that we don't have any other characters in here that turn into magical slopes. So this is our grid. Our starting location is on the top row, the empty space. So let's figure out the space, the start, yeah. Is it the same for our input? Do we need to find it? No, it's just first row, second column. Go away, thank you. First row, second column. So what does a path algorithm look like? We don't need to do depth first. We need to do exhaustively. We need to exhaustively figure out every option, I guess. I don't actually know if there's a longest path algorithm. Let's do a quick Google. It's a simple path because it does not contain loops or repeat vertices. It's NP hard. Ooh. So probably it's going to be a smart grid. It's not a random grid we see here. There's a limited amount of paths because it's a pretty difficult problem apparently. Okay, so we have two constraints. One is if we hit a slope, we need to go in one certain direction. The other one is no loops. So let's take that into account once we start building out the algorithm. We are again going to need neighbors. I think I've wrote that function 10 times already, but I'm still going to do it an 11th time. So our parse, this is our parse, right? I'm going to extract this in a function. Yeah, and let's have a type. Grid. It's just an array 2D. It's an array 2D of characters, sorry, or of cells. And this is how you type an array 2D. So this returns grid. Yeah, okay, everything is green again. And now let's write some neighbor functions for a grid. So, or next, yeah. So given a location and a grid, and location is maybe good enough. We need to know what's at that location, but that's constant. We can look up stuff in a 2D matrix really fast. So yeah, let's just look it up ourselves. So it's a grid. Or let's first return my 4 orthogonal directions, whether or not taking the out of bound thing into account. So for example, we could do one above, if r is bigger than 0, then we can return that one. Then we can yield this. That my formatter is not helpful right now, so yeah. Okay, so now I'm just generating the offsets. So, and I'm always making bugs at off by one thing. So let's test this in a second. Length 1 of the grid. So if my grid is 2, is the maximum index is 1. So it has to be smaller than this minus 1. And then we can do this, and it's the same for the columns, probably. So if column is positive, we can go 1 to the left, and if column is smaller than length 2, then we can go right. Let's try this out. Yeah, grid next works on any, so it's a generic function, so we can play around with just matrices containing values or numbers. We don't have to work with cells, that's a bit easier. So let's put this in a 2D matrix. And let's find some neighbors. Yeah, let's find some neighbors for this. So let's put that in a variable. And let's find neighbors in this grid for 0, 0. We're almost there. We need to map those offsets we get to, so it's the delta, and we need to map that to the actual resulting location. So that's offsetting R by DR and offsetting C by DC. This will work better. I'm already rusty on my graph algorithms. That's great. So we get 2 back, 1 below, 1 to the right. That sounds right. Let's take 1 to the right. That looks correct. That looks correct. That also looks correct. Let's make our matrix a bit bigger to see if we can get all 4 cardinal directions out. So that's the middle. That should give me 4. 1, 2, 3, 4, and that looks potentially correct. I'm good. Let's wrap a test for this. I don't want to forget that. Let's quickly put that here, and let's move my tests to the bottom so I can test all the things. So yeah, we are testing that we can grab stuff out of this matrix. Let's maybe put that matrix as a temporary variable and do a couple of tests. Yeah, so let's do a quick check by hand. I'm not gonna write all of those again. I'm just gonna write a couple of them so it looks like it works. That's the worst kind of testing. I see this at my job all of the time. Like you see that there's some tests and some coverage, but once you take a look, it's like the easy, happy path, and all the tricky parts they have been like completely skipped. Yeah, that's saying something. It's like we tried because we had to, but we don't really like testing, or we don't see the added value, or there's too little time, there's too much pressure. But that's most of the times. If I see like stuff like that, there's some testing, but the interesting cases are not covered. That's most of the times like symptomatic of a bigger problem in a team or in an organization. And maybe time is the problem, maybe money is the problem, but there's always some kind of problem in that case. Anywho, we can figure out next, or at least like figure out the 4 different neighbor locations. That's not really interesting. I want to make it a bit more interesting, as in also include the slope logic here. So if we're on a slope, we only have 1 next neighbor. So I'm gonna write a new function, next cell, given a grid and a row and a column. That should just be next. So that should be the same, but we filter it. Or no, we don't have to filter it actually. We can say let cur is grid at RC. Let's pattern match on that. Yeah, let's pattern match on that. So if it's a slope, we need to filter, and otherwise if it's a forest, we can never be at a forest, right? So we have to filter those out as well. Filter out forests and slope, but that's a bit of a tricky thing. We need to only return 1 direction or 1 neighboring location, right? So if we are on a slope, we have only 1 neighbor. We can figure it out in a second. If it's a forest where we're on right now, we should crash hard. I'm standing in a forest. Should never happen. And if it's... What's the other thing? What's the other thing? Path. Okay, path. That's logical. If it's a path, we can just do the next thing. And let's type our grid. My compiler is confusing me, so probably the compiler itself is confused. There we go. So sometimes you have to give type hints. But anyway, so the slope thing we have to do, we have to figure out like, or we'll probably always be able to go off the slope. There won't be a forest killing us, right? Are there slopes that slope into a wall or into a forest? Doesn't look like it. Maybe in our input. Let's double check. Don't see any problem cases here. No, I think we can assume that following a slope will never crash into a forest. Let's assume that for now. Cool. So if we are on a slope, our next cell is super easy. So it's falling down on the slope. So let's write a helper function. Yep. So it takes a grid and a slope, and depending on, or you know what, I'm gonna keep the slope thing in there to make it really clear that we're working with slopes. That's because we got rid of, or we didn't parse, we only parsed into a slope, but not, we still have the character, that's what I mean. So I'm gonna pass that around as well, so it's super clear that we're working with slopes here. So this should be, let's wrap a list around it over here, and this generates like the location to the right of me. So that's column +1. This should all match up nicely. Why is there so much red in there? Okay, it's gone. So we can do this. We can do this. We can do this, which increases our row count. And we can go upward as well. Where is that character at? Right there. Which decreases our row offset. We go 1 up. Let's put a catch-all in there. We should never be here. We didn't check this when parsing, so let's do that here. And let's put the problem case. Let's output that as well. So cool. So back to the next self logic. For slope, if we have the assumption that we can always slide down a slope, this is okay. We only have one neighboring location or one next cell, which is falling down the slope. In a forest, that should never happen. So let's maybe put a guard clause in there. That's the first thing we should check. And if it's just a path, we generate our neighbors and we filter out everything that is forest. So forests we don't want, everything else we do want. Oh, those are locations. Yeah, we have to look up. We have to look up locations. So this is generating row columns, but we need to know, like, is there a forest at that location? So yeah, this was a bit of a trying too much in one line. So let's put some variables in. So this is the possible neighbors, and let's filter those. So I'm going to do exactly the same, but this is a row and a column. Now we can dig into the grid, row, column, and pattern match on that. So if at that new row column thing, maybe that's a weird or a bad choice because we're already using R, so we're aliasing or shadowing. Don't want to do that, so let's make it very explicit. It's a different variable. And if it is a forest at that location, we don't want it, so that's what I was trying to do, but now correctly. And if it's something else, it's okay. Whoa. I don't know what my formatter was thinking, but there we go. Let's get rid of that variable because that looks weird now. So we have this calculator for neighbors with the bounds check, yes. And then we have, what the hell, everything indented weirdly. Okay, sorry. So yeah, we do the bounds checks here. We do the slope thing here. We have problem cases, and we get rid of everything that is forest where we cannot end up in here. So I think we cover everything neighbor-wise. So I'm hoping our next cell thing works. I can't believe how much auto-formatting has failed me. Okay, we're back. So yeah, we have a grid, a start location. Let's figure out next possible states from the starting location. Given our example, that should be only one valid path. This is not correct. Is this correct? Why am I seeing this and this? Oh, sorry, this is the second row. Yeah. Oh yeah, so we have only one valid neighbor for start here, which is the one below. So let's see if that works. It's grid dot next cell, given the grid and my starting location. Yeah, so that gives me something. Let's take a look at that thing itself. Should have a bit more options. Should it have two? Whoa. So if we're here, we could go up or we could go right. Yeah, we should be able to go up to origin or to start and right. Yeah, that looks correct. So this is me exhaustively checking whether or not my algorithm is correct. But I'm quite confident. So let's keep on keeping on. If you know this quote, shout out in the comments below. It's pretty niche. So we have our next, so we can calculate next locations. I think we are ready to start working on our longest path algorithm. That takes a location. Let's maybe rename this function to next cell z, because that is actually more correct. it's a plural kind of thing. So next cells. Yeah, so say we are given a node and the grid and maybe some visited states. That's what we're also going to need. It's just a list of locations we have already visited for the no loopy or no revisiting nodes things. Sets are great for that kind of stuff. And what do we need to do? We figure out the next cells. I'm already writing my algorithm here, so I'm naming this current, not just start. We figure out all the probable next ones, and then we could put it in a queue like breadth first, or we can do recursion like depth first. It doesn't really matter, so let's do the easy thing. Famous last words, but let's do the easy thing and let's do a recursion here. So I am going to put this in a function. So it's a let longest path given a grid and some state. And our state is the current and the set of visited nodes. So we calculate next, then we recursively, so let's make a recursive function. We need to a halting condition. Sorry, I am jumping. I am jumping from one thing to another. I'm a bit chaotic today, I know. But we also need like a finish. Let's figure that out in a second. But if we hit the finish, so if current equals finish, we're done. Oh, and we also need to know path length, which is basically visited length, right? It's not the path because it's unordered. We don't know if it's like jumping from the one node to the correct node, but the length should be our path length. That's how I'm going to implement it at least. So yeah, if we hit our halting condition, then we know the length of the path. We need the longest path. This is not the longest path, right? No, so in the recursive case, so here we have next, and then we're going to say let distances equals longest path of grid current. No, we need to map over next for every next node. And we need to recursively do a longest path calculation for the same grid with the next node. Finish stays the same, and I need to add whatever current to the set of visited nodes, or next. We are visiting current, I guess. And set empty is not correct, and then we need to do a singleton set containing current, or the start position at least. So yeah, then we know the distances of the recursive longest path for my neighbors. And actually, if I put in some kind of accumulator, length up until now, we can just feed that in here. So it's length up until now. And then here, and +1, sorry, because we just took a step. And here we can just say length +1 as well. Is it +1? I'm not sure. I'm not sure about this one. But okay, then we have a list of lengths and we need the maximum length. So let's return that. And we don't need that variable. Future me does not need any readable code. Why is this length not a number? Unit. Why is length unit? Don't know. Okay, probably because I was missing an else. Probably because I was missing an else, yeah. Okay, this is good. I'm not sure about those 1+1+. I think I might have written a bug or two. But let's play around with it a bit. So longest path, given the grid, and start node is 0, 1, always. Finish is no clue. Visited is, let's call it start. Now let's put that in there and let's use those variables instead. So we can put start in there. We figure out finish in a second. Our visited set, and our initial length is, I guess, 0. We start at start, so path length. That's actually a node. We're gonna be off by 1, off by 2, off by 3, but we'll get there, I'm guessing. We need to figure out the location of the finish, which was the bottom right thing. Is it the same in my input? It very much is. So we need to know the last row. Yeah, we need to know the grid dimensions. So what's the last row? For our example, what is it? Too much to... I'm just gonna play around with it. So let's grab everything in some row, and this is where we're gonna play around with. So it's the grid array length 1, array to D, sorry, length 1. Is this possible? No. Is it one less than this? This is how I figure out my off by 1 things. So yeah, so this is the last row, and there it is. So yeah, let's just do this. It'll probably be the same to grab the last column. But we don't need the last column, we need the 1 to last column. So this is the location of the finish. Yeah, so this is our finish. Very roundabout way, but this way at least I don't have to think and I can watch it happen. I'm using my computer for what it was made, to calculate stuff for me, to compute stuff for me. So we know start, we know finish, let's fill that in. And now let's try to fix our off by 1 or our probably 3 off by 1 errors we have here. Pretty sure this will not work first go. There we go, lots of crashing. I was not expecting a crash, I was expecting a wrong result, so interesting. Looks like a Stack Overflow, right? Yeah, if things explode with a stack trace that is this long, that is very much a infinite loop. How can we have an infinite loop if we have visit? Oh, I'm not using my visited set. We should discount impossible paths. Like if we don't reach the finish, but we have no more neighbors, we should stop walking. This is an invalid. So I'm gonna put an option in there. And I'm gonna choose here. So we only keep the sums. And if we hit like an impossible path that will never reach the finish, we can now, why is this not working? Let's choose. This choose should return a list of U's, yeah? U is int. Why can I not do list.max on a list of ints? Oh yeah, I should wrap that in a sum. No, my return type should be an option int. That is an option int. What's the problem here? I'm not seeing it. Oh yeah. Choose gets rid of the option type. So let's not. Yeah, what am I trying to do here? So we have options, we have a list of options here, and I want the maximum sum if there is one. So yeah, I'm gonna do that with a little help. I don't know how to do it in one line, so that's distances, and those are all the distances that have sum. So now we can do if next distances if we have some, then we can say give me the max one. Otherwise, none. And that's an int, so that should be max, wrap that in a sum. Okay, this, I think we can rewrite this in a more elegant way, or I'm pretty sure. I'm still not using visited. And I'm still not filtering out invalid paths, but let's take a quick zoom into this here. How can we elegantly write this? First or default, yeah, I'm taking a look at this at or I'm thinking about this with a C# head because I've written a lot of C# this week. Try-head will very much be something we can use. So we can do list.map. And then, you know what? Let's do that afterwards. Let's first make it work and then make it right. So yeah, let's back to choose. Because I'm jumping all over the place and it's even hard for myself to keep track. And that's never a good sign. So breathe in, breathe out. Okay, now we can continue with hopefully a bit less chaos. Two things we need to do. Take visited into account, and if we have no next neighbors to go to, we have hit an incorrect state. So if next list is empty, then nope, otherwise. And we can do the same thing for our visited. So else if visited set contains current that's not the right thing to do. We should do that differently. Let's do that here. Yeah, let's filter out this thing. Let's make a set of lists and let's do a set difference of that minus, yeah. So let's do a set difference of, no, what am I trying to do here? I'm trying to filter the next cells. I'm taking too big a step again. So this is a list of next cells. If we have none, we're done. But we don't need to take everyone into account. If we already visited next, we can go. Or we can do the same thing on current. But then we can't add current here. We need to add current somewhere else. Yeah, let's filter them out here. So these are all the next neighbors. And let's just do accept. Yeah, I'm not going to write it super performant, but that's not a problem. So list.accept. And then visited set to list. So that's not the most efficient way to do the difference. But performance is something that comes after we have it working. So we filter out everything we already visited, and then we have everything covered, I think. Famous last word. Let's take a look. Sum 96. That sounds off by 2. I predicted this. But where is the 2 thing? Let's. I can start like randomly changing stuff, but that does not sound like a good idea. So let's take a look again. If current is finished, then sum length. I think that is not needed in there. 95. Okay. Where am I doing +1 as well? Here, but here we need it. So maybe my initial length. I think maybe. This is correct. At least we see the right number. So let's just try. Yep, I'm gonna grab everything, put it after the tests, which we have not written any of, except my indexing or my next neighbor thing. So let's parse the input. Let's see if that works just as well. Looks about right. Interesting. Why would that crash with an infinite loop? That's actually something, come again? Why would it work for my example? And why would it crash hard for the input? The finish was at the, what is this, day 23? Oh, I saw it, damn it. Stop filing. Yeah, it should be this. Yeah, that's 140 by 139. Yeah, I think that's correct, actually. Then why is this happening? I'm gonna do it one more time to actually inspect my stack trace, because I'm a bit lost right now. So let's clear our console and let's do that one more time. Third time is the charm. That is a really hard thing to say for a non-native English speaker. All the ths and the ts. Anyway, why is this crashing? Stack Overflow. Why is it not halting? It could be that it's a pretty deep search, a pretty big graph. Because if it works for the example, barring any exotic bugs that happen only on like super specific things, it should be working. How? This is not that trivial to troubleshoot, right? Those depth first things never are. What's the way out of here? We only have one interesting function, which is longest path. All the rest is pretty straightforward. We could wrap some tests around that, but I'm not convinced that the problem is in my next. We tested that a bit, fall down. We had an assumption that we could never fall into a forest, but we checked that here, so that will probably be fine. Yeah, looks correct, Longest path. If we're done, we're done. If we're stuck, we're stuck. That also works. This is the heavy recursive call. Can we make it tail recursive? No. Or we have to work breadth first. We could rewrite to breadth first. It's not really that hard once we have our algorithm, right? We don't care about performance. We just shove the next things on a queue. Actually, that would be doable if we treat our state as a queue and the current finish stays the same, so we can pull finish out of here. Current visited length, that changes for everything in the queue. So let's pull finish out of there. And let's rewrite to breadth first. He said as if it was like a 2-second kind of thing. Actually, I think it might work. We don't need any priority queues. We don't care about efficient searching. We're looking for the longest path, so we don't need to sort all our paths by any kind of heuristic. So I'm just gonna use a list. Instead of this, I'm gonna wrap my things in a list. So this becomes the queue. And it's int by int, a set of int by int, and an int for the length. And that's a queue element. And a queue is a queue element list. So this list, let's inline that in a single type. So this is a queue. And let's grab this. Let's say we have a queue here. And let's destructure. No, let's pattern match first. So match queue with, if we have no visit. Oh yeah, this is actually gonna be cool. If we have nothing, we have nothing. If we have this, where is it? Where is it? There it is. Grab this. So let's quickly pattern match on the queue. If it's empty, we're done, and we have found nothing. Yeah, sure. Will that work? Yeah, it'll work. Rest of the queue, and now we can do the thing we were doing. So this is a quick rewrite to breadth first. Expecting a tuple of length 4. Oh yeah, that's not correct. It's current. Oh, I should put this first thing in there. There we go. Yeah. So we're rewriting to breadth first. If we have no work to do, we don't do anything. If we have work to do, we do the work. But instead of doing this, we need to provide the queue. So this is the this is the things we need to create. So let's do this. Let's do this. So these are the next elements in our queue. These are next elements in our queue. This should be a queue. We should, what is next again? A list, so we can just map. Why is this giving this much trouble? Okay, there we go. So then we can recursively call our function, longest path, and we give it the grid, the finish, and our queue is updated. It's the next queue with the rest of the queue. So we expanded the first element into all the other bits and pieces. Yes, what's this thing doing here? What is this thing here? Oh yeah, we still need to max. That's true. So let next distances. Actually, we don't, right? Do we? How does this work? How does this work? I'm almost there, but now how do I find like longest path? We need to know, we need to not stop here, right? If we have like other elements here, we have some length, great. But we need to do this for everything. So yeah, we're almost there, but not quite. This is where we need to do the recursive call now as well. So this is expanding the queue, and this is finding a hit, but we also need to process the rest of the queue. So that's it. I think if we started with breadth first and not did depth first and then did the rewrite, we would have ended up in an easier place. But okay. I'm going to, next to the queue, I'm also going to build an accumulator with a sorry, with a lengths so we can max. So here we can do max. So these are all the lengths we have found if we hit a finish. So this grows the accumulator. So it's a length with accumulator, but we need to go recursively here as well with the rest of the queue. So grid, finish, egg, and the queue, the rest of the queue. So I think this might, no? Yes, what's the problem here? Int option, but as type int. This can be an int. I'm not married to options in my end result. It's a list of int, sorry. Oh, this is where the int option was coming from. There we go. What's this thing? So we are working, we have elements in the queue, and we have no next neighbors. Then we can just do the fallback to processing the next element in the queue, right? I think so. All branches of if must return values implicitly. Okay, we're missing an algorithm argument here. So I have grid, finish. I should have my ACK in here. Has ACK changed in any way for this branch? I think not. Famous last words. So yeah, I think we can put this in a queue. And our initial accumulator is empty. Ta-ta-ta-ta. Should work. It should definitely not work. Why is it saying... Okay, there we go. I was not running all my code or not sending everything to Rebel. So let's see if this still works, for example, because we took one broad sweep without verifying anything. That's a dangerous thing to do. Does this still work? 94, it actually works. I'm actually amazed by that. I'm pretty amazed by that. Let's see if this works without blowing our stack. Oh. Now it might just like infinitely. Now it might just infinitely. I don't know if that's better than immediately blowing our stack. How could we be blowing our stack? I don't actually. Oh, we have an answer. Stop thinking, start copy pasting. Ooh, that's nice. I'm actually pretty amazed how relatively easy the rewrite from depth first to breadth first went. And trust me, it was as chaotic for me as it was for you. I would not want to maintain this code. But we got there. Part 2 will probably be something tricky. I'm gonna quickly read it and yeah, if it's an easy fix, we'll try it, and otherwise we're gonna end here for today. As you reach the trailhead, you realize that the ground is not as slippery as you expected. You'll have no problem climbing up the steep slopes. Now treat all slopes as if they were normal paths. You still want to make sure you have the most scenic hike possible, so continue to ensure that you never step onto the same tile twice. What is the longest hike you can take? This sounds like a really... It will explode our search space or a search tree, but it's actually a super duper easy fix, right? We just replace our slopes by paths in our input grid, and we run our algorithm again. Famous last words. Yeah, let's give that a try for the example to see how bad it gets, how many paths we have. So copy paste. I'm gonna copy paste my file as always, so I don't have to think about maintaining part 1. it just works because it's in a different file. There we go. Clear everything. Let me maybe run the example again. That should still give us 94. And now let's do one more round of mapping on our input grid. So if everything goes well, this is the only change we need to do. If it's a slope, it's a path, and otherwise we keep our identity. So we got rid of all our slopes here. And it should, for the rest, our algorithm should stay exactly the same. 166. Oh, that is incorrect. Huh? How can I find something of length 166? Actually, we should never get here. So we're only doing this thing. Let's make sure, let's get rid of those things and see it crash. It should not crash, but so we have this. We should not be falling down anymore. Yeah. Yeah, this should still work. Or still give me the wrong result. Yeah, it is. So interesting. 166 is not something we were expecting to see. I'm going to print out my path. Yeah, I'm going to print out my path and put that next to the... Oh, I don't have my path. It would help if I had my path and not my... We can keep track of the path instead of the length. We could do that. We could do that. Let's see if we can do that. So, my accumulator is a list of locations. Oh yeah, no. It's a list of oof. Yeah, no, it's not as easy as I thought it would be. So no, actually stumped. Why is it working for part 1? And if I do this simple change, everything breaks. That is actually, I'm super confused. In the example above, this increases the longest hike to 154. Why am I seeing 166? I'm going to print out my... No, that's... I am repeating myself and coming to the same conclusion that it's not super easy to do. Yeah, I'm going to cut the video here. Part 1 was cool, was fun, was chaotic. Part 2 was tricky, so I'm going to have a little think on it and see where the problem is. But we're hitting in the hour, so I'm gonna do that off camera. This was Additive Code in F#, day 23. Very chaotic, did not solve part 2 yet, but we'll get there in the end. Thank you for watching, and I hope to see you again next time. Bye-bye.